Now, the problem that we are going to talk about today are very, very complex. In fact, you will not understand most of them. Okay? And so, so my goal today for you is not to explain the whole problem so that you can go and try to solve it at home. It will take several years to even completely understand the problem. I will try to explain at least one problem, give a lot of background behind it so that you can understand to the extent possible, right? You will not understand 100%, it's okay, right? Don't get disappointed that, oh, it's too hard, but I want you to appreciate. I want you to appreciate the kind of problems that they exist. And at least the one problem that we're going to explain, you probably get 50% there. You may not understand 100%, but you will at least see the beauty behind it. That's really the... And maybe as you grow up, as you go to high school and college, some of you, I'm pretty sure, you will pursue this, and maybe one day one of you solve these $1 million problems. And I will be your biggest champion if you do that. Okay? And your parents will be very happy. But you will be more than happy for yourself. Right? Well, so just appreciate these problems. You had a question?
Oh, could you solve them?
No. If I solve anyone who solves them, I won't be here. If you solve this, you'll be one of the most famous mathematicians of the generation. Right? And you will get a field medal, which is the equivalent of a Nobel Prize, and you will get $1 million. But if you really solve, right, $1 million is probably the least of your rewards. The rewards will be a lot more than that. I'm not just talking about money. In fact, out of the 7 problems that we talked about today, one of them was already solved by a Russian mathematician. And you know what? He refused to take the $1 million. And that's an interesting story by itself. We'll talk about that. So when you reach that level, money is not your only criteria, or may not be even the main criteria. You will do it because you love to do it. And your name will be etched in the history of mathematicians forever, for later generations. So if you do it, Sri did this, Sri invented us in new mathematics, right? So that's a much bigger reward. Because, hey, a lot of people make $1 million. How many of them are remembered? We don't remember all of them. But why do we talk about people like Fermat, or people like Archimedes, or people like Srinivas Ramanujan? Not because they had $1 million. They didn't have. In fact, Srinivas Ramanujan was a very poor man.
Yeah, and then he got accepted to get to cure America, and then because he didn't get in school.
Yeah. So he lived very poor. He was working as a clerk in a small office. But on the side, he was doing some of the cutting-edge math that was not solved by anyone else before that he solved, right? Just sitting in a clerical office. And if you know the story of Einstein, I don't know how many of you know his story, his early story. After finishing college, he did not get a job. He did not get a job for a while. With somebody's recommendation, finally, in the Swiss patent office, patent is when somebody invents something, those patent clerk, he actually records them all. Somebody tells, okay, you are eligible to get the patent, he records them and he gives that. That's a reasonably dull job, if you think.
It's monotonous.
Monotonous job. But sitting there in his spare time, he discovered one of the greatest scientific theories ever, theory of relativity. He wrote a paper in 1905, about 100 years back. And that changed the way we think about the world, right? So, it doesn't matter what you do. And some of you probably might become mathematicians, but most of you will not become mathematicians, which is fine. But whatever you are, don't forget these beautiful stories behind it. And maybe on your side, at your spare time, maybe you solve one of these problems, right? Not just because you want to make $1 million, it's a cool money to make, but because you love to do it and you will be remembered forever, right? So with that, let's go to this week's $1 million math problems, okay? All right. So we love stories, right? Who doesn't like stories? So let's start with another stories this week. So this story happened in the year 1900. So at the beginning of a new century. in the year 1900, and the setting is Paris in France. Anybody visited Paris? Some of you, right? It's a beautiful city, and everybody remembers Paris for the Eiffel Tower, right? But there's a lot of other stuff. But it was an August day, it was a hot August day in France in the summer of 1900, and over 200 of the brightest mathematicians from around the world gathered there in a conference center. And they were actually attending what is known as the International Congress of Mathematics. It happens every 4 years. Some of the mathematicians who do a lot of interesting work, they come together, meet once in 4 years to present what the work they are doing. Other mathematicians review that, and a lot of interesting stuff goes on there. And while that's going on, one particular mathematician, a German mathematician, his name is David Hilbert. He's from the University of Göttingen in Germany. That's it. The University of Göttingen has a lot of interesting story in mathematics. It is one of the greatest universities of that time. Even today, it's a pretty well-known university. Some of the greatest mathematicians came from there. We'll talk about them in a while. David Hilbert is from that university. He came there to the International Congress of Mathematics, and while he did something different from everybody else. What he did was, everybody is presenting what work they are doing, what problems they are solving. He said, look, we're at the beginning of a new century. Let's review and talk about what are some of the greatest unsolved math problems as of today. Okay? Not the ones we are solving right now, but one of those greatest unsolved math problems today, and perhaps kind of set an agenda for the century. And so he compiled a list of 23 of the greatest unsolved problems as on year 1900. Greatest unsolved problems. Unsolved math problems. Now when we say math problems, sometimes math problems are solved for the sake of mathematics. It's called pure mathematics, right? You may not know why or how it is useful for the rest of the world. Oftentimes, rest of the world finds a use for it later, right? But sometimes many of the math problems come from other fields, from science, social sciences, maybe economics. And the problem exists, and now if you solve the problem, you will take, let's say, physics. There's some problem forms for physics. You will take the physics to a new level, right? So but irrespective of whether it's a pure mathematics problem or a applied mathematics problem. And applied mathematics is something that is required for other fields, right? Like a science or social science or thing like that. Whereas pure mathematics is for the purpose of pure math itself. So he compiled a list of 23 greatest problems, unsolved problems as of the year 1900. And interestingly, most of them got solved during the 20th century, right? At the beginning of the 20th century. And the people who solved them are like the who's who of greatest mathematicians in 20th century. So it did actually set an agenda for the 20th century mathematicians. So most of them are solved, except one. So this one great problem, okay, all of them are solved, or actually some people prove that it is unsolvable, which is also acceptable, by the way. But you have to prove, you can't just give examples why. So there's some problems are completely unsolvable, and that's also accepted as a solution if you could prove methodically. Okay? But except one. This one problem becomes part of our next episode in the story. This one is actually, in fact, while it was not solved in the 20th century, by the year 2000 it is still not solved. Even when this was proposed, that particular story, that particular problem, of all the 23 problems, was David Hilbert's one of the favorite problems. In fact, he was asked, after you die, 500 years after you die, if you wake up from your grave, what would be your first thought? And David Hilbert said that if I wake up from my grave after 500 years, my first thought would be, is Riemann hypothesis solved? That is the one unsolved problem. It's called Riemann hypothesis. Now, we'll talk a little bit about Riemann hypothesis. It's a very beautiful problem, just like Fermat's last theorem that we talked about last week. And as Hilbert predicted, Riemann hypothesis is still as unsolved as of today, of all the problems that we proposed. But he said that is the problem that will be most interested to know if it is solved not in 100 years but 500 years. So he thinks, and as of now it is still unsolved. So what is Riemann hypothesis and who is Riemann? Now, interestingly, we'll come to that. But before that, let's go to the next episode in our serial. Now we are in the year 2000. Okay? So in year 2000, we are at the beginning of a new century. In fact, we are at the beginning of a millennium. Right? So now the scene has changed. It is actually on the May 24th of year 2000. The scene has changed to Boston, Massachusetts, United States. Interestingly, look at the locations. This was Paris, France, and now in a century, the interesting event that we are going to talk about is happening in a different place. What do you think in the matter of a century, geographically speaking, history-wise, what has changed? Not related to math, but in general. If you look at France, if you look at what's happening over here, where this is happening and where this is happening. Shri?
Each millennium, they change the continent that I think is on.
Yeah, it can actually, every 4 years it happens, it could be a different place. This is actually not International Conference of Mathematics, but it's a different context, but where the agenda for the next century is being discussed. At the beginning of 20th century, probably the greatest continent, the most powerful continent is Europe, right? And probably the most powerful country, most people would say, is England at that time, right? England is kind of, it was not at the peak. By 1900, it's kind of already weakening, but for the previous 200 years, it kind of the powerful. And at the beginning of 20th century, still, Europe certainly is considered as the most powerful continent because they kind of ruled or ruling a large part of the world still at that time, right? India was colonized, a lot of Africa, South America was colonized. So it's happening in Europe appropriately, and a lot of mathematicians are from Europe, right? David Hilbert is from Germany, which is also in Europe. What do you think happened in the history in the course of 20th century in terms of power shift? Yes.
Soon the United States of America started becoming more and more powerful, and England started getting weaker.
Right. So, yeah, good point, right? So what happened in the 20th century is two great wars happened. World War I and World War II, which kind of shifted the balance. The United States has been becoming more and more powerful by the time, and it continued to grow, but the two world wars literally broke Europe. But the United States, totally, especially after World War II, is clearly a superpower, and it still is. So it's interesting that the setting kind of shifted. So you might think it every 4 years it might happen in a different continent, but it also, who is defining the agenda? At the beginning of the 20th century, Europe was still defining the agenda, right? But beginning of the 21st century, by the time US is clearly defining the agenda. Just an interesting observation, not related to math. So what happened at this time? So there is an institution called Clay Mathematical Institute. It's called Clay Mathematics Institute. Clay also, you can just call for simplicity, simply CMI, Clay Mathematics Institute, or CMI. it's an organization that promotes math. Not just the regular simple school math, but on advanced mathematics, promoting advanced mathematics and how mathematicians solve them. They give awards and prizes for those who solve really important problems. And they said, now we're at the beginning of a new era, new century, let's, just like David Hilbert did 100 years back, let's compile a list of the greatest unsolved problems. But to just make it a little bit more interesting, a little bit more spicy, we'll not just compile the list of the problems, but we'll also give $1 million prize for every single problem. So whoever solves this, any one of these problems, they'll get $1 million. And they identified 7 such problems. And we are going to talk about those 7 problems today. So those are today called millennium problems or $1 million problems. Isn't it cool? If one of you solve those, make $1 million. But the first thing would be you need to understand what those problems are. And many of these problems are very abstract. So it will be hard for you to even understand, but I will try to make it, give it some background and make it interesting, at least with one problem, right? And the most famous of those 7 problems, in fact, today what is considered the greatest unsolved math problem is Riemann hypothesis. We'll talk a little bit more about Riemann hypothesis and I'll try to give at least some background so that you know what it is about and maybe one of you will take it up. Yes, Steve?
But what if, like, one of those problems don't have a solution?
In fact, if you can prove that there is no solution, that is a solution too. But you have to prove, you can't just say. You have to mathematically prove why there can never be a solution to that. That's a proof, that's a solution. That will be accepted. In fact, if you can disprove it also, that's accepted. If you can prove that this is, for example, we say hypothesis, we use the word 2 times often. Okay, let me read this. When it comes to math problems, unsolved math problems, we use one of 2 terms very often. They're called either hypothesis or conjecture. One word. So the word hypothesis or conjecture. What that means is that they're unproved. A hypothesis means a statement that this looks to be true, but it's not proven. Same is conjecture. If it is proved in mathematics or science, they're called theory. Now, sometimes theory, people say, oh, it's only theory, but theory means it is proved. It's accepted by the peers, other mathematicians and scientists as true. It is proved, right? Others have reviewed it, they accept it. So the ones that we are talking about today are either hypotheses or conjectures. So that's why it's Riemann hypothesis. It's a very beautiful problem. The whole story behind it is really interesting. So what is Riemann hypothesis? Now, as I said, you're not going to understand most of these problems, so I'll give the statement first, but don't get scared. Okay? Then I'll try to give a background behind it and explain. And you'll still not completely understand it, but I'll give a little bit of background. You'll at least appreciate what is it talking about.
Doesn't it have something to do with prime numbers?
Part of it, yeah. Yep, we'll get to that. So Riemann hypothesis. So first, let's write down the statement of the problem. And don't get scared if you don't understand, because you will not. So the statement of the problem goes something like this. The real value of all non-trivial zeros of the zeta function are on the critical line. Okay. Who did not understand this problem? You did not raise your hand, means you understood it. right? Okay, you're right on track because you're not supposed to understand. Okay, even I did not fully understand it, but I understand it a little bit after spending a lot of time on it. Yes, Varun?
What's a zeta function in critical line?
Good questions. We'll get there, right? But before going there, in fact, I need to explain what is real value, what is not trivial, the zeros. In fact, you think you understand zeros, but the word zero is not used in the way you understand it. We'll come to that. What is zeta function? What is critical line, right? So all of them are Greek and Latin right now. And some of them are actually Greek. Zeta is a Greek alphabet, but it's a function. But I just wanted to put the statement, so don't worry about the statement. We'll come back when we finish the background information. I'll check if you guys understand even part of it, okay? So let's come back to what is the background. What is it all about, right? To do that, we need to go a couple of centuries back in time. Okay? In fact, we need to go, the first part we need to go really back in time. And it actually starts with what Sri mentioned earlier. It's something to do with prime numbers. So prime numbers. Most of you know what is prime numbers, right?
Yeah.
Okay, who can define prime number? Yes?
A number that can be divided or number that can go by itself by 1 and itself only, not any other number.
Excellent.
That can be multiplied.
Right.
Not
A number that has factors of only 1 and itself, no other factors. You cannot divide evenly with any other whole number, right? Everybody agrees with that? Probably all going to the same, right? That's the prime number. So most of, anybody who does not know or still does not understand what is the prime number? Good. So if you understand prime number, you are right on track to understand Riemann hypothesis. So let's write down the first 100 prime numbers. Okay, I'll take your help to write it down. Okay, you tell me, I'll keep writing.
Okay.
Let's start with, what is the first prime number?
2.
1.
2.
What's that?
Is 1 a prime? Somebody said 1. Is 1 a prime number?
No.
No.
1 by definition is not. Now you can debate it actually, but we'll debate, keep the debate for some other time. So mathematicians define that 1 is not a prime number. So let's start with 2.
No
Okay?
other even numbers.
3.
2 is the only even number, even prime number. Next,
3.
3,
3,
5,
5.
5,
7.
7,
11,
11,
13,
13,
15,
No.
17.
17,
19,
19,
23.
23,
20, no,
27.
29. 27 is not a prime.
Yeah.
27 is 3 cubed, 3 times 9. 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79,
81.
83, 89,
Yeah.
97. So there are 25 of them. Of the first 100 numbers, 25 are prime numbers, right? Well, so what? So here is people who are curious minds, right? Some of these mathematicians have very curious minds. They keep asking questions, and a lot of math and science starts from those curious questions. That's why it's very important. Keep your curiosity up, because most of the greatest inventions and discoveries start with a simple question. So one of the questions that was raised was, how many prime numbers are there? Would they stop after some time, or would you always find?
Infinite.
Okay, to answer the question, mathematicians try to understand what we call the density of primes. So, you guys know what is a density? Warren, what is density?
Like density is like how much matter is within a single object.
Right, how much matter is there in some object. So, mathematically speaking, how densely packed are the prime numbers in different ranges. So, for example, we found that in the first 100 numbers, there are 25 primes. But if you try to find how many primes are in blocks of 100, let's say. So, up to 100, 1 to 100, okay? Then 100 to 200. So, 101 to 200, up to 201 to 300, 301 to 400, 401 to 500, 501 to 600, 601 to 700, 701 to 800, 801 to 900, 901 to 1000. Okay? If you want to find how many primes are there, well, we're not going to write it, it's going to take a while, so I'll just give the numbers. So, we know 1 to 100, how many primes are there?
25.
25, we just talked about that. 101 to 200, there are actually 21 prime numbers are there. 201 to 300, there are 16. 1 to 4, there's 16. 1 to 500, there's 17. 501 to 600, there are 14, 16, 14, 15, and 14. Well, is there anything that you can tell based on this?
I see no pattern.
What is, you see some pattern? What is the pattern?
I said I don't see any pattern.
You don't see any pattern. Right? There's no clear pattern because they seem to going down and going up a little bit. But one thing that we can generally say that there is a general thinning down as we go up, although it's not always true, right? At this level at least. Well, just to prove that, let's take it to one more level. Okay? This time what I'm going to do is, we'll actually, instead of going in blocks of 100, we'll go by multiples of 10. First 10, first 100, first 1000, first 10,000, first 100,000, first million, first 10 million, and first 100 million. We can keep going, but I'll just stop it here to save the time. Okay? And how many primes are there? Yes, Steve.
My question about that.
Blocks of 100, okay?
Yeah. Why do they have a different number? Like, why don't they have 25 always? Because they're going by 100.
Good question. Why don't you? Well, so general thinning down is somewhat intuitive in the sense there's something called sieve of Eratosthenes. Anybody heard about sieve of Eratosthenes?
The what?
It's called sieve of Eratosthenes.
Sieve?
Remember we talked about Eratosthenes a while back?
Yeah.
The guy who found the circumference of the earth using sticks and sun shade. So it's called sieve of Eratosthenes. To find the number of primes up to any number, the actual prime number, there is a method. And to do that, you take the numbers and you divide it by all the prime numbers less than that. And as you go up, what happens is there are more prime numbers that divide it into it. So if you can see that even within 100, if you look at the in the first 10 numbers, how many are prime? 4. So in the next 10, also there are 4, right? In the next 10, there are only 2. In the next 10, there are only 2. In the next 10, there are 3, right? In the next 10, there are 2. In the next 10, there are 2. In the next, there are 3. In the next 10, there are 3. In the next 10, there are 2. In the next 10, there is only 1, right? So, although it's not consistent, you can see that there is general thinning down, right? What happens is, as you go to the upper numbers, when you are in the first 10, to find a prime number, you try to cancel all the numbers which are divisible by previous numbers, right? When you go up, there are more numbers to divide into, so there will be more composite numbers. Composite numbers are those which are not prime, right? So there will be more composite numbers, meaning the less prime numbers. So there is that's why there is a general thinning down, right? And let's see if that is true here, because here we can see that this is general, but we can't see the pattern clearly. But let's go into multiples of 10 and see what happens. The first 10, how many primes are there? We just talked about 4. In the first 100 of how many primes are there? 25. The next, in the first 1000, how many?
14.
We don't know, but it is 158. In the first 10,000, there are 1,229. In the first 100,000, there are 9,592. In the first 100,000, there are 78,498 primes. In the first million. In the first 10 million, there are 664,576 79 primes. The first 100 million, there are 5,761,455 primes. Okay? Well, we can see that the number of primes go up as you go up. But to really observe the pattern, let's do one more thing. Let's do what is called a density of the primes. And what I mean by density is how densely packed the prime is. To get that, divide the number of primes by the total number of numbers, right? So 4 divided by 10 is 4 times or 0.4, right? You guys know decimal numbers?
Yeah.
Okay. 25 divided by 100?
0.4.
0.25. So divide 25, not 100 divided by 25, 25 divided by 100, right? 160, all that you have to do is put a decimal point. So 168 divided by 1000 is 0.168. 1229 divided by 10,000 is 0.1229. This is 0.09592. It's not 0.9592 because there's one additional 0, right? So 0.09592. This is 0.078498. 0.066459. 0.05761455. Now we can see a more clear pattern, right? As we go up by every multiple of 10, there is a clear thinning down of the number of primes. Do you see that?
Yeah.
We went from 0.4 to 0.25 to 0.168. The number is reducing. Do you see that? Do you understand? And we can keep going and we'll find the pattern. Yes, please. Yeah, sure. So, this was observed a long time back by a lot of mathematicians. Okay? And the question that we asked earlier, that if there is a general thinning down, at some point, would the primes thin down so much that there are no more primes? In fact, over 2000 years back, Euclid, remember the Euclid, the famous Euclid who wrote the 13 volumes of Elements? He actually proved that the primes will go forever, won't stop. So that question is answered. Okay? But mathematicians won't stop with an answer, right? They ask the next question. We see that this general thinning down. Is there a way to come up with a formula, some kind of formula, to come up with how many primes are there in a range of numbers? Now we know that you cannot, in fact, the question that actually bugged mathematicians is, there is a clear lack of pattern, right? While some prime numbers, if you look at it, after 47, next prime comes after 6 numbers, right? After 53, also there is 6. But the next one comes within 2, right? And the next comes after 6, the next one comes after 4, the next one comes within 2. The next one comes again 6, 4, 6, and this one doesn't come until 8, right? So how do you, from any number, when the next prime comes, is there a way to find the next prime? In fact, so far nobody found it. In fact, if you find a way to predict the next prime number, for sure, you will be one of the great mathematicians. Okay? Nobody could find that part. But if you can't find that, the question that many mathematicians try to find, especially this, a lot happened in 16th and 17th century, is there a way to come with at least an approximate number of primes in a particular range? And one great mathematician, going back to University of Göttingen we talked about, his name is Carl Gauss. Anybody heard about Carl Gauss? Yes, some of you did. Very good. So Carl Gauss is a great German mathematician. In fact, he's considered one of the greatest mathematicians ever. He's the one, if any of you attended a math genius class, we talk about his story when we used in the time machine to his, when he was a 10-year-old in a classroom. And he actually came up with a great mathematical solution to a very simple problem that is unsolved until at that time. A simple formula for if you had 1 plus 2 plus 3 plus 4 plus 5, some of the natural numbers up to any number, and instead of adding is very easier to find. And some of you probably know the answer, right? He's the one who discovered that when he was a 10-year-old, like some of you in a classroom, right? And so there's a great story behind him. But he went on to become one of the greatest mathematicians. And he was a professor of Göttingen in the beginning of 19th century, 1800 to around 1800 to 1850s and 60s. Carl Gauss came up with actually a formula. And again, you will not understand the formula itself. The formula itself you can learn later when you grow up. But he came up with an approximation. It will not be the exact number, but he said the number of primes, and it just purely based on observation, he came up with that. Because this, as there is a general thinning down as you go down by multiple of 10, this is called a logarithmic scale. Anybody heard about logarithm? Some of you did. And probably most of you heard, but you don't know what it is, right? A logarithmic scale is if you draw a graph, right? So if we have a scale of 1, 2, 3, 4, or maybe 10, 20, 30, 40, 50, and you're trying to find, draw something, maybe temperatures across different days, you can come up with a graph. A logarithmic scale will be slightly different. The distance from here to here is 1 unit, let's say this is 1. Within the same distance, when 1 unit, the next one will be 10, 100, 1000, 1000, 10,000, 100,000, etc. So, with every increase in unit length, you are multiplying by 10. That's called logarithmic scale. So, based on this pattern, Carl Gauss identified that this looks like more like a logarithmic scale. So, he came up with this. The number of primes up to a number is approximately equal to, if x is the number of numbers, right? X divided by logarithm of x. And it is remarkably true. It's actually so closely true. So don't understand if you don't know logarithm, you will learn probably in high school or so. But just appreciate. And there's some of the advanced mathematics. Yes, Pranay.
Can you say logarithm or a logarithm?
Logarithm. Logarithm. And the story of logarithm is itself an interesting one, but maybe for some other class. Yes?
Like, what's the difference between a logarithm and a logarithm?
There's nothing like a logarithm. There's only a logarithm.
There's an algorithm.
Algorithm is completely different.
From the
This is logarithm, and there's also a word called algorithm, which is completely, oh, now I know what you guys said. Algorithm is a procedure, a mathematical procedure to solve problems. That is different. A logarithm is a scale, is a way to represent numbers. Okay? And often in math we just write as log, L-O-G times the logarithm. Okay? So x divided by log x is the formula that he came up with, and this is called the prime number theorem. So Carl Gauss solved this problem of a formula, an approximate formula to give the number of primes in any given range. That's called prime number theorem. Prime number theorem. Okay? Now this is happening in the 19th century, the early 19th century, the 1800s. That's when Carl Gauss proved. Carl Gauss was, by 1850s, considered one of the greatest mathematicians ever. He's placed along with Archimedes and Newton, as these three are considered three of the greatest mathematicians at any time. Okay? So what is all this to do with the Riemann hypothesis? We'll come there in a second. Okay? But do you guys followed up to this point?
Yeah.
I didn't lose you yet, right? Okay. I try not to, try to keep it simple so that you can follow. Okay. This is one, by the way, Bernard Riemann. Who's Bernard Riemann? Bernard Riemann, well, it was the first time I told his name, I guess. Riemann hypothesis was proposed by Bernard Riemann. Bernard Riemann is actually a young man when Carl Gauss was a renowned professor. So he also entered University of Göttingen. So he, in fact, one of the reasons why he went to University of Göttingen is because Carl Gauss is over there. Carl Gauss was one of the greatest professors, greatest mathematicians of that time, at any time. So Bernhard Riemann is a young gentleman in 1850s when Carl Gauss was probably already in 60s or 70s at that time. So he entered University of Göttingen and he took this to the next level. But before going to that, there is another part of mathematics which is completely unrelated to this, and Riemann actually put them together. Yes, so you have a question? Okay. Steve?
Is Bernhard Riemann the same person that we in the Math Genius class? Is
Yeah, the same one. Well, we visited in our time machine, right?
Yeah.
Yeah, it's the same Bernhard Riemann. So, you guys understood at least high level until this point? Right, Pranay takes lots of notes. And you guys feel free to take notes. A lot of it is there in the handout, but sometimes you remember better when you write it down. So feel free to take notes. Good job, Pranay. Okay, but it's more important you appreciate it, right? Even if you don't understand every word I said, so like things like logarithm, I don't expect you to completely understand yet, but at least, get a general idea. And completely unrelated to this, another field of mathematics is developing. And that is the interesting thing about a lot of great mathematical theories or mathematical developments. There are many fields that independently develop, and then someone comes and relates them in a completely unexpected way. And we saw many of them, and we are going to see more of them today. Like Pythagoras' theorem was completely came for the right triangle, and then Diophantus asked the question, can we take it to higher powers like a cube or a power 4, and then Fermat generalized it because mathematicians like generalization. And what I mean by generalization is, if you solve one problem like x squared plus y squared, x squared plus y squared equal to z squared, right? That is the Pythagoras theorem, like 3 squared plus 4 squared equal to 5 squared. Well, so there are a lot of research done by Pythagorean school, and they showed that this is actually a right triangle. This is 3, this is 4, this is 5, 3 squared plus 4 squared is equal to 5 squared, or x squared plus y squared equal to z squared for every right triangle. And someone asked, well, why stop at square? Why not cube? How about, are there anything for x cube plus y cube equal to z cube? And why stop at cube? X power 4 plus y power 4 equal to z power 4? Are there any solution to that? And that's why the great Fermat's last theorem story developed last week, right? Ashri?
Did Andrew White, did he found a solution for x and y and z, or did he find a solution for did she?
He actually proved that there are no solutions for this.
Oh, okay.
Right? And which is what Fermat said. Fermat said that as far as you know, in fact he said he found a proof that there are no whole numbers meeting this. And then Andrew Wiles finally proved it. Right? But this is what we call a generalization of this problem. Right? When some theory is proved, mathematicians want to take it to the next level by making it more general. Now what happens over there is you will get more powerful problems, but they will also become less concrete, less related to the real world. We call them more abstract. That's why they're harder to imagine, right? Because there are too many variables, right? You keep adding variables, harder, but they also solve more complex problems and take advanced math to the next level. The same thing happens. So we talked about the prime number theorem and the whole prime number theorem. Prime numbers are probably one of the most fertile ground for number theory research. Number theory is a field of mathematics where the whole numbers, the properties of whole numbers are researched, and prime numbers is a great place to research that. But completely unrelated to that, a new field was going on for hundreds of years before Riemann. What Riemann did is he took both of these together and came up with something, combined them, and took the math to the next level. So what was the other part? The other part was an interesting problem by itself called Basel problem. Basel problem. Now, Basel is a city in Switzerland. And there lived a very well-known math family. And what I mean by math family is there is a family of mathematicians, generations of mathematicians who did advanced research in mathematics in different fields. Sorry. And we talked about some of them in the last few classes, if you remember. Anybody remember Bernoulli family? We talked about Bernoulli in probability, in calculus, in algebra. They actually did a lot of research. They're like grandfather, father, son, grands. There are a lot of them. They worked on mathematics generation after generation. So math flowed in their blood. And one of them, Bernoulli, is Bernoulli by the name Jacob Bernoulli. So Jacob Bernoulli asked an interesting problem. They lived in Basel. That's why it's called Basel problem. The problem that he asked is, look at this, 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared, etc. When I put those 3 dots, that means going infinitely forever. Okay? So if you take this problem, can anybody find the value of this? Infinite series are hard to solve, right? They're going forever. Now, one thing that we can do is, we can take a calculator today. In those days, there's no calculator, but you can still, brute calculation you can do, and you can keep adding 2 times first, 3 times first, 4 times first, 5 times first, and you can come up with an approximate value, right? But you cannot know for sure what is the total value, right? But the question that he asked is, do you think this, as you keep adding up to infinity, do you think the sum of this value will also keep increasing forever? Or do you think it's going to never go beyond one value? Is it going to, what we call it, go in limit, it reaches a particular value? And many people tried, and they actually thought it's going to stop at some value. Because as you keep adding, after some point, it keeps increasing. But as you can see, the denominator is increasing. The total number is increasing by smaller and smaller and smaller and smaller and smaller and smaller numbers. So it's increasing by so small a number that eventually it may never cross a particular value. In fact, if you use calculator and try to find, you can see that it will stop somewhere around 1.64 something. It will never cross beyond that. But what is so special about that number? This problem was solved by one of the great mathematicians which we talked about many times. He's a very prolific mathematician, Euler. You guys remember Leonard Euler? He came in so many math classes, right? He did so much research. He's an 18th century mathematician. He actually proved this, that its value is a surprise. In fact, when he solved this and gave the value, it shocked, literally shocked most mathematicians. Can you guess what could it be? It's actually, he proved that it is pi squared divided by 6. Where is pi coming here? You take whole numbers or fractions of squares, and when you add all of them up to infinity, you get pi squared by 6. Now pi, as we know, as we talked about in another class earlier, is related to the circumference of the circle divided by diameter. Where is this coming? That's the beauty of math. In fact, after this, mathematicians believe that the nature speaks itself in math. It's more strongly believed, right? You may not see the patterns, but if you understand the underlying beauty, things you think are completely unrelated, they're actually related. We just did not see until then, right? So, until then, pi was known only in terms of circles. Now we proved that it is actually happens to be sum of an infinite series. This is called an infinite series, and he did not actually stop there. He actually proved a general. Remember mathematicians like generalizations? He took it to the next level. He actually proved this for not just this, but any. If you take any of the series where, if you take an even number as a power, like 1, 2 power 4, 3 power 4, 4 power 4, 5 power 4, if you keep adding forever, and its value found it to be pi to the power of 4 divided by 945. In fact, he came up with a general rule for all what do you think he's going to do next? What do you think he's going to put in the exponent?
6.
6. Good. 3 power 6, 4 power 6. And he has also had a formula value for this. But if you keep adding, how do you think we can generalize this? 2 power, what do you think we should put to generalize it? And there you go, Sachin. So mathematicians try to put a variable so that it's not just for 2, 4, 6, but for any where n is an even number. Now, he found it only for even numbers. He could not find anything for any odd numbers or other numbers. But for any even number, he came up with a general formula. 4 and 5 power and etc. And you can actually find a value, whatever it is, right? I'm not interested in giving those values at this time. You can find it, you can actually research, Google research and find it. But actually, Euler not only solved the Basel problem, he actually gave a general solution for any infinite series where this kind of infinite series where n equals to even number, there is this solution for it. Now, if you guys want to do some research and actually as you grow up, maybe prove an unsolved problem, one thing that you could do is do it for any odd numbers. Because as of today, there is no solution to any odd number. Not only that, Euler could not find it, nobody found it so far. Now, we do know that we can actually find their approximate value, which is like, no, it is equal to 0. Blah, 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 blah. But no math, why that number, it is called irrational number, you get an irrational number, is it related to pi or something else? Nobody found a general rule for any odd numbers, except of course 1. When n equal to 1, what happens is, okay, when n equal to 1 happens, this formula, this series becomes 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. Right? Because when n equal to 1, 2 power 1 is 2, 3 power 1 is 3, 4 power 1 is 4. This one is an interesting series by itself. It comes so often in physics. This is called harmonic series. And the reason why actually it's called harmonic series is very interesting. It comes very often actually in music. That's why it's called harmonic series. If you take a string, okay, if you think, let's say this is a string. If I do this, what happens is it actually vibrates. Particularly if you take a piano string or a veena, any of the string instruments. If you do that, you know they vibrate. The vibration that comes out of it is actually follows the harmonic series. Remember we talked about nature expresses itself through math? That's how music itself expresses it through this harmonic series. That's why it's called a harmonic series. Now mathematicians proved long time back that this particular series does not have a finite value like this. By the way, this kind of series where the value will approximate to a particular number like this, they're converging. Converging means they are getting closer and closer and closer to one particular value. Actually, this will never become this number, but you get closer and closer and closer as you keep adding, right? This is called converging. One second. And the mathematicians proved that this particular series diverges. Diverges means this will keep increasing forever. It will not converge to any particular value. Okay? So, this generalized the Basel problem. Okay? We know that it converges for everything except when n equal to 1. Okay? It converges for all n greater than 1. When n equal to 1, it diverges. Okay? Now, we're talking about whole numbers greater than 1. Okay? That's an interesting thing by itself. You had a question, Sri?
I have a question, but it's about Fermat's last theorem.
Do you want to wash your face and come? Yeah, go on, Sri.
Fermat's last theorem.
Mm-hmm.
If it wasn't x, y, and z, it was x, x, and x, that x would be 1.
Do you think so? So x power n plus y power n, x power n plus x power n equal to x power n?
Yeah.
No.
Why?
X power n plus x power n is 2x power n.
Oh yeah. If it was multiplication, it would
Yeah,
be
exactly. Be very careful. But a good observation. I'm glad you're thinking, right? Always think for other sorts of problems. Okay, good. So, this is a whole different research going on in the 17th and 18th centuries, and a lot of scientists like Bernoulli, Euler, and others contributed to this. And this actually very closely related to calculus. In fact, this is the when you keep adding things up to infinitely and then go to a particular number, that's called limit. And the limit is actually at the core of calculus. What are called differential calculus. But we'll learn about that later. We talked about calculus a little bit earlier, right? So this is another way to look at calculus. Now, so what is this Ruth Riemann's work? What is this to the prime numbers, right? So these two big streams of work are heavy research in the 18th and 19th century, and then enters our hero of the story. Well, who is the hero of the story? Bernard Riemann. You guys forgot? So Bernard Riemann enters the story in the year 1859. So middle of the 19th century, the University of Göttingen. By the way, that time around mid 1800s is a very interesting time in the history of Germany. Anybody knows history? What goes on in the
It made a country?
Yeah, so Germany was one of the last nations to form, one of the large big nations to form in Europe. Remember we talked about in the old days, there were no countries. Initially there was a Greek, in Europe especially, there's a Greek Empire, there was a Roman Empire, then when Roman Empire disintegrated in the around 5th century AD, there will become a lot of local regions that have got formed, but around mid-second millennium, maybe around 14, 15, 16, 1700 years AD, what we call as nations or countries today got formed. England, France, Italy, they all got formed based on their languages, their culture, etc. But Germany did not get formed until by middle of the 19th century yet. That itself is a great historical story. Yes, maybe we'll talk about that in actually one of the Imaginous classes, but you can also go and research. It's a very interesting, maybe you in the middle of high school you might learn European history, it's an interesting story. So this is the time when Germany started integrating. Until then it's like 300 different kingdoms or principalities finally comes together in the 1850s. And so it's interesting times in Germany. At this time enters 1859 our hero Bernard Riemann. Now I call him hero, but he's a very shy man. Now similar to Andrew Wiles who we talked about, I don't know why these mathematicians are shy. Right? He wants to do his own work. He does, but he presented a paper. A simple, actually, 10-page paper. In mathematical standards, 10-page paper is fairly small. He presented a paper and posed a question which, as of today, is considered one of the greatest unsolved math problems, known as Riemann hypothesis. So what did he say? Well, this is what he said, but what does it mean? So remember, we talked about this particular series, 1 plus 1 over 2 power n plus 1 over 3 power n plus 1 over 4 power n, 1 over 5 power n. And at this time, Euler and others are mainly talking about whole numbers. And some people said, why do we stop at whole numbers? We can consider the same problem for also rational numbers, right? Which are like fractions. Well, why stop there? We can also do it for all real numbers. Anybody knows what is rational numbers? Yashri?
It's like fractions.
Right. So all those numbers which can be expressed as a fraction of two different whole numbers are integers, they're called rational numbers, like fractions and decimals. Now, if they're rational numbers, how about irrational numbers? Irrational numbers are those which cannot be expressed as a fraction of two different whole numbers, like pi. Okay, like pi, it cannot express it as an exact fraction. There are approximate 122 by 7. You might think it is pi. It's actually an approximation to pi, right? It cannot be expressed as an exact fraction. As a decimal, it will keep going forever. Yes.
How many irrational numbers are there? How many irrational numbers are there?
Infinite. So square root of 2 is another irrational number. Square root of 3 is square root of actually any non-square number. Cube root of any cube root number. They're all irrational numbers. When you include both rational and irrational number together, they're called real numbers. Okay? So other mathematicians started applying this series because it's a very interesting series. Started applying to other numbers because when you start from one set of numbers, mathematicians like doing what? Generalization by solving bigger problems. So this is more and more general by applying to different numbers. Well, then comes Bernard Riemann in this paper. He said, well, why stop with real numbers? Okay? Do you guys know any numbers that are beyond real numbers?
Exponents, maybe?
Exponents, they are still real numbers. 2 squared is 4. It's a, right? So, there is a whole different field that you actually will learn this in high school. They're called imaginary numbers or complex numbers. Now, if you don't understand again, don't worry, just leave it at this point. But if you take a number like square root of, we took square root of 2, we said it is an irrational number. But how about square root of -1? So, in our real experience, the square root of any negative number has no corresponding reality. Okay? So, that's why you can't find them. Like pi we can find, square root of 2 we can find. For example, if you take a right angle triangle with the lengths of 1 and 1, this length is square root of 2. Though it's a rational number, we can see it in reality, right? For square root of -1 or square root of any negative number, we could not find a real consequence. And so, but some people might say, okay, then if it is not, there is no real value for it, discard it. Why worry about it? But mathematicians look for ways to solve. And they gave it a name. They call it an imaginary number. It's imaginary because you can't find it in reality, but it's still sometimes a useful number for mathematical development, especially when it comes to solving some of the algebraic problems. And they gave it actually a name to keep it easy, simple. Square root of -1 is odd thing to write, right? So they just call it I. So if you have square root of -2, what do they do is, that is same as square root of 2 times square root of -1. So you can call it square root of 2i. Right? Whatever. So your 2 times square root of -1 can be called 2i. Now, all of you saw number lines?
Yes.
There is a 0 here, 1, 2, 3, 4, etc. Right? And on this side we have -1, -2, -3, etc. Right? This is a number line we are all familiar with. This is called a real line also. The reason is, any of the real numbers you can actually plot on this. For example, where would pi come? This. Between 3 and 4. It's actually right after 3 because it's a little bit more than 3.14, so this is where pi will come. Where do you think square root of 2 will come? Where is it roughly equal to 1.41, something keeps going, so it will come somewhere here. So this is square root of 2. Similarly, all real numbers, whether rational or irrational, or fractions, half will come here, 4.5 will come here. You can put negative, if you want negative 3/4, will probably come here, right? All real numbers can be shown on this line, okay? But how about the imaginary numbers? Now, you cannot find them here. So mathematicians came with an interesting thing. Well, why don't we plot that on a vertical line like this? And all imaginary numbers, so if it is a square root of -1, it will come here, and we can call it I, because they gave it a name called I for imaginary number. And if there is 2i, square root of -2 will come here, and you can even have a square root, negative square root of -1, which is, you can call it -I, it can come here, right? So you can keep extending. So now, if you have any number which is a combination of both real number and imaginary number, they call it complex numbers. And again, if you don't understand all of it, don't worry, you will learn this actually in high school. Okay, so you still have a lot of time for that. Some of you have a lot of time, some of you probably learn in the next couple of years. But so these complex numbers are a combination of real and imaginary numbers. So for example, you can put 3 plus 2 times square root of -1 or 3 plus 2i. This is a complex number. How can we plot it on this graph? So 3 comes here, right? 3 comes here and 2i comes here, right? 2 square root of -1 comes here. So you can extend this, So this point is equal to 3 plus 2i. So this is called complex number. So you take any real number, and this is called the real part of the complex number. This is called the imaginary part of the complex number. And that's what he meant by real value here. Okay? We'll come to that. So what Raymond said is that let's take this particular infinite series, but let's not restrict n to just a real value. Let's take it for any complex number. The complex number is combination of real plus imaginary. And this is where it gets complex, right? This is where it gets harder because it's difficult to it's become so abstract that it's difficult to understand. That's why these math problems are harder. But as you grow up, your ability to understand abstract things will grow up. In fact, if you want to become a mathematician or scientist or any advanced field, actually, one of the important things is the ability to understand the abstract things that most other people don't understand. But that's how you solve more important problems and you invent or discover new things. Like if you look at Albert Einstein's theory of relativity, it's so hard for most people to understand because it's so abstract. We do not see in a day-to-day life. For instance, the light travels at a certain speed, nothing else can cross it. What do you mean? How can you see it? Right? No, you can't see a light ray going at a whatever speed. And in fact, you could think that it is infinite speed. You say, no, it's not infinite speed, actually an exact speed. How will you measure it? Those are so abstract. But to think about them, you develop abstract reasoning skills. And this helps in understanding. But if you don't understand, in fact, how many of you did not understand everything I said so far? Most of you, right? In fact, all of you. In fact, if you understood all of it, well, you probably are weird, right? You're not expected to understand all of it. But if you understand only a little bit, that's great, right? I think if you just appreciate a little bit, okay, that's good. Because maybe as you grow up, as you go to high school, college, some of you try to understand more of it, and maybe one of you solve this. You know what? If you solve this, you'll of course get $1 million. That's cool, but you won't care about $1 million really if you reach that level. Because as I said, one of the 7 problems was already solved, and the person who solved the problem, he would refuse to take the $1 million.
Can you get to that?
Huh?
Can you get to that?
Who did that?
Yeah.
We'll talk about that. It's a Russian mathematician called Gregory Perelman. Not this problem, but one of the 7 problems. He solved it, but he refused to take $1 million because see, when you reach that level, you would not do just for money. Money is, of course, useful, right? But the rewards that you get are much more than money. Yes, Steve?
What year did
Gregory Perelman solve? We'll come back to that. I don't know. It's a little bit of distraction. We'll go to the other 6 problems. Now, because, do you see why explaining them is difficult? So I'm just giving a background for one of the problems. So I'll give a background for one of this because this is probably the greatest of the 7 problems, unsolved problems. So, but others, I'll just give you a glimpse of it, and hopefully you can study more about it later. But at least one, I hope you will get, at least for this, you get a little bit of background. But now, what did Raymond do? He said, in this N, and he actually uses the letter S. Doesn't matter, you can use anything, but he used S. But so we'll use the same thing that he used, respecting him, right? But he said S can be any complex number on the complex plane. This is called complex plane. Okay? And why is that important? And he gave a name to it. He gave it a name called zeta function. And this is where the zeta, somebody asked what is zeta, right? This one is called zeta. He called it zeta function to zeta of S. S is called argument, that is a variable. So, and today we call it Riemann zeta function. He just called it zeta function, but because Riemann defined it, we call it Riemann zeta function. So, it is the same function that we talked about earlier, but variable, the exponent is now any complex number. Okay, that's called Riemann zeta function. Yes, what?
Like before he made the plane with complex, like a complex numbers, were imaginary numbers considered to be on a different plane?
So he's not actually the first one to define the complex plane. It's a different branch of mathematics. Other mathematicians started defining that it's a useful concept. Yes, it was there before him too. But he was probably one of the first to use it effectively to define a problem. So what he did was, is there a solution for this? Well, that's not actually a solution. We called it a zeta function, right? For this function, let's try to at least understand a few terms from this problem, right? The real value means if you have 3 plus 2i, which is a complex number, 3 is called the real value of non-trivial zeros. We'll come back to non-trivial zeros of this zeta function. This is called the zeta function. Or all on the critical line. Now we'll come back to what is critical line. Okay. So if you go back to the complex plane, okay, this is 1, 2, 3, 4. For a second, actually, forget about complex plane. Just look at this line. Okay, this is the real line, this is number line. We are all familiar with number line, right? So what happens for this number line for this zeta function? This now, if you are only talking about this line, basically these are real numbers. We ignore the imaginary part. When n equal to 1 or s equal to 1, we said that this diverges, means it has no value. You cannot define the value. It keeps going increasing forever. Right? When n equal to 1, this is not defined. But we said, if you remember, for any n greater than 1, it always has a value. Right? Euler proved that. For n equal to 2, he proved that the value is equal to pi squared by s, pi squared by 6. For n equal to 4, he proved that this pi to the power 4 divided by 945. Different for, although there is no exact formula for 3, we knew that it converges to a particular number. For any n greater than 1, we know the exact value of this function. Okay? At n equal to 1, this is not defined. Okay? Actually, n less than 0, it doesn't diverge. But mathematicians have found a way to actually, they do transformations to define these as well. But then Riemann came and added the complex plane. And when he added complex plane, so he added this. Right? And then this kind of becomes, for all values of this n greater than this, Riemann zeta function is defined. Okay? Again, if you don't understand, don't worry. Right? You will see this picture. If you Google research for Riemann's hypothesis, you will get this. Okay? And probably when you go to high school or college, you can understand better. But I just want to give you a picture, because picture you remember better than words. That's why I'm giving the picture. But you won't understand this completely. That's okay. So for all this right of this point, you can actually find the value. And using the transformations, you can also find these values. But in algebra, what we do is, if you take any function and make it equal to 0, okay, and you want to find the value of this s or x for which it is 0, those are called, solution to this problem are zeros of the function. When you say zeros of a function or zeros of any series like this, for what values of s will this be 0? And now we knew that to the right of this it will never be 0, right? We just found different values. But mathematician did found that for every -2, -4, -6, etc., the zeta function will become 0. But they also defined what is known as, and Raymond defined, we called this, where it's half line. This is 1, right? This is 1 and this is 0. The middle of this is, we call it the critical line. And what you ask, what is critical line? So in Raymond's zeta function, if you draw it a graph, we call this line has half as zeta. Here is what was proved, that all these zeros, well, these are called -2, -4, every negative even number. It so happened that the zeta function is 0. So these are called trivial zeros. Trivial zeros because we know that for sure that these are zeros. But what we don't know for sure is that, actually what we do know is that all other zeros happen in this is called critical region. All other zeros happen here. But what we don't know, but what Raymond proposed is that all of them happen, all these non-trivial zeros happen only on this particular line, where this is corresponding to real value of the zeta function equal to half. Okay, that's what it means. Again, if you understood this, you are weird. Okay, so if you did not understand, you are right on track. But hopefully you understand a little bit, right? And you will understand more later down when you go to high school and college if you go back to this. So the real value of, because the real value of the complex numbers of all non-trivial zeros, these are called trivial zeros, all the non-trivial zeros which you know that lie in this particular region between 0 and 1, of this zeta function, this is the zeta function, are all on the critical line. He said they are going to be all on this line. Now what he did not do is prove it. He said that it is an hypothesis. From that time, a lot of mathematicians tried to prove it. Now you would wonder, why is it so important to prove that? I mean, it looks so abstract, you don't even understand why is it important. It's important because this has everything to do with the prime number problem that we talked about earlier. So this will, if Riemann hypothesis is proved, for example, wrong, all the what goes today cryptology, if you go to NASA or any militaries, they use very complex passcodes. Security systems, internet and security systems around the world will fail if this is wrong. That's a big deal. So it has a lot of applications. Now, because all the security systems and the passcodes, the complex, I'm not talking about simple passcodes on iPhone your dad puts and you want to break, right? My son wants to do it all the time. So I'm not talking about that passcode, I'm talking about really the complex ones which are used by government and military and NASA to secure things. They are based on prime numbers. And the fact that prime numbers are completely random. If Riemann hypothesis is proved wrong, actually prime numbers will not be random, and which actually breaks the course, right? And it has many other, in fact, if Riemann hypothesis is proved, many other mathematical problems will be automatically proved because they are dependent on it. And that's what happens over a period of time. Many fields of math that get developed independently, like prime numbers theorem, we saw that, or the Basel problem in the complex, they're all completely different fields of mathematics, but they all came together in Riemann hypothesis. And now, the actual scientists, mathematicians found many other mathematical theories that are actually related to Riemann hypothesis. If this is proved, many things others will be proved as well. So, as of today, this is considered as the greatest unsolved math problem. If you can solve it in your lifetime, not tomorrow, not today, not tomorrow, not in the next week or next year, in your lifetime, okay, you are in for a great ride, and you know, you'll definitely get a field medal, which is equivalent of a Nobel Prize in mathematics. You'll definitely make $1 million, but more important than that, you will be remembered like the way you remember some of these mathematicians. of the billions of people lived on the earth, we remember only few names, maybe few hundred or few thousand names. Right? In mathematics, we talked about Riemann, we talked about Carl Gauss, we talked about Srinivas Ramanujan, we talked about Hardy, we talked about scientists like we talked about Euler, Bernoulli, Archimedes, Carl Gauss. Well, your name could be right next to them. But it's not going to be easy, right? Now, in fact, just like Andrew Wiles had his dream when he was 10-year-old, like some of you, it's probably just a dream at this point, but hopefully 20 years down the line, you'll turn your eye onto this and may understand and solve. But the important thing is there are many things like this. Keep your curiosity. Keep your eyes open for this and try to, and even if you don't fully understand, appreciate that there are bigger things and the beauty behind them. Look at that, for example, we're talking about even if you don't understand the zeta function, if you understand the Basel problem, the fact that it is equal to pi squared by 6, that surprised the entire mathematical community when Euler found that, right? Isn't it surprising why pi squared by 6 pi comes there? That's because math is very intrinsically beautiful. If only we go a little bit deeper than the school math, right? Now, to go deeper than school math, first you need to do your school math. Oh, I only do the school math, you will not understand this, right? First you need to understand complex numbers, which you will be learning in the school. But to understand complex numbers, first you should understand real numbers. Or to understand real numbers, first you need to understand rational numbers, or fractions. To understand fractions, to be able to do fractions well, you need to do whole numbers, right? You need to start with simple 1 plus 1 equal to 2, like every preschooler starts. From there, you can go to fractions. From there, you can go to irrational numbers, you can go to complex numbers, you can go to vector calculus, the advanced math, you can go to Riemann hypothesis, but it all starts with simple math. So, when you go to school and you are asked to learn how to divide a fraction, it's boring. Well, it's not boring. It's boring only if you don't understand that there is a lot of interesting things behind it. But to go with this, first you need to do your simple math. Make sense? Okay, so that's Riemann hypothesis. And as I said, if you completely understood it, you're weird. But if you did not completely understand, but probably appreciate a little bit, hopefully, that I hope that my job is done, right? But one day, maybe some of you come back to try to solve it. In fact, I'm so fond of this particular problem, of all the math problems, we'll probably start a Riemann club. How about that? We'll start a Riemann club and we'll have all the kids, starting you guys, but maybe all the high school and math college kids, who wants to solve Riemann problem one day. We'll start a Riemann club and come up with try to understand it more and maybe solve it. Right? Wouldn't that be cool? We'll start that. Okay. But let's also try to understand, well, not understand, talk about the other problems a little bit, right? So the 6 other problems, one of which is solved, but other 5 are not solved, well, total 6 not solved, including this. And we do not have time to go into this much in depth for them. They're actually even more abstract than this. So I will not try to explain them, okay? Like I did this one, but I'll give its name, I'll give the names of those, and probably give a very brief background. And if you are interested, you can do a lot of research. You can Google research. In fact, you can go to this particular website for Clay Mathematics Institute. So just Google for Clay Mathematics Institute. And on their website, you will find lots of, in fact, all the 7 problems explained with some examples, in some simple terms, as simple terms as possible. You can find more details about the 7 problems I'm talking about, okay? So let's talk about the other 6 problems very briefly. And then we are going to watch a video, right? You guys love movies, right? We'll watch a movie of, especially Riemann hypothesis and more background behind it. But, so the second one is called, so this, the sequence in which I'm going is, I'm not following the same order as given by Clay Mathematics Institute to make it somewhat easy for you, but order is not that important. So the first one is Riemann hypothesis. The second one is called Young, Mills, and mass gap, which means nothing to you. Right? Now, Young and Mills are two physicists. Is something, Gaurav?
No.
Okay. Young and Mill are actually two physicists. Physicists means scientists who are working in physics in the 20th century, a few decades back, in the 30s, 40s, I think. And this is deeply related to physics, especially the subatomic particles. You guys, some of you, Nandita, I know you're a fan of subatomic particles. If you always want to talk about physics, you can tell everything about all the little particles, right, Nandit? Yeah. He always talks about those. So, Young and Mills did a lot of research and came up with some theories related to quantum physics. And say, yeah. See, he's so excited. So it's a very interesting field, but it's also very abstract because it talks about also about atomic particles that you can't see. You can't even see on a microscope. You can only understand their properties mathematically, right?
Switching through want to make straight lines.
Yeah.
When you heat up.
Maybe you can take one class one day for us. So, so it's related to quantum physics, and in quantum physics, Young and Mills introduced a new theory, new concepts to describe it about half a century back, to describe the particles in terms of geometry, in terms of geometrically describe them. They came up with the concept, and they found what is called a mass gap. A gap in the mass of the subatomic particles, which still exists today. This is not an unsolved problem. So how to solve that mass gap is this particular problem. And if you solve this, you probably have to discover and make some new mathematics, but also some new concept related to physics. And you will take both physics and math to a new level if you solve this problem. It's one of these greatest unsolved problems today. Okay? So if some of you like Nandit, who's interested in math, probably this is the problem that you should attack one day. Young, Mills and mass gap, remember that. So the third problem on the set of 9 problems, this is called P versus NP problem. P versus NP problem. This one is related to, so this one, I'll just write the field name. This one is related to quantum physics. No, the second one is related to quantum physics. The third one is related to computer science. P versus NP problem is related to computer science. So those of you who are interested in computer science may want to attack this problem one day. So an NP problem is something like, there are n cities, there are n number of, or x number of cities, and you want to visit, find a way to visit all cities in a sequence without visiting any 2 cities in sequence. There are n number of cities, and you visit all the cities without visiting no 2 cities, no 2 cities which are next to each other consequently. Okay, that kind of problem, you can start with the 4 cities, 5 cities, 6 cities, etc. It is hard to solve, even with a specific one. But if you generalize it for n number of cities, it is almost impossible to solve even with advanced computers. It will take forever, right? But if someone gives you a solution, this is how, you can also take things like perhaps, okay, there are you have 4 by 4 matrix like this, or maybe we can write like a matrix, and this is a 3 by 3 matrix, and you want to combine, you want to connect them with different points, okay, but without no two dots are in a straight line, no 3 dots in a straight line. You can be either horizontal line, vertical line, or diagonal line, okay. It will take actually, for 3 by 3 probably, you can solve after some time. 4 by 4, 5 by 5, 6 by 6, 7 by 7. In fact, I have an exercise like that for your project, it becomes harder and harder. Now, if you generalize it to n by n, remember mathematicians like generalization. If you generalize it to n by n, it is virtually impossible even with the supercomputers. It will become so complex, right? Those kind of problems are called NP problems in computer science. Now, if somebody gives you a solution, I say this is a solution, you can easily verify whether it is right or not. But to solve and find all the solutions is virtually impossible, right? Those kind of problems are called NP problems, and P is related to those. So, so what is P versus NP problem is to determine whether every, and again this is a little bit of abstract language, every language accepted by some non-deterministic algorithm, you can figure out it later, in polynomial time is also accepted by some deterministic algorithm in polynomial time. So that's the statement of the problem, which you should not understand. But that's solving the third problem. Yes?
What's the second?
The second one is called Young-Mills and mass gap, and it is related to the quantum physics. The third one is called P versus NP problem. In fact, if you were to go to type P versus NP, you get millions of links related to this. All of these are very famous problems in mathematics. The fourth one is called Navier-Stokes equation. Navier-Stokes equation. So Navier and Stokes are two equations actually. Two scientists of 19th century, almost 200 years back. They came up with an equation, a set of equations that describes how fluids behave. Fluids, do you guys know what are fluids?
Chemicals? Water.
Water,
Liquid
air,
soda.
liquids. So all the liquids and gases together are called fluids. When we say fluid, everything that is not solid, they are liquids plus liquids and gases, both together combined. So water is a fluid, so is air. So the behavior of fluids like water and air is described by Navier-Stokes equation, but it's not true. In fact, if you prove this, we'll make great advances in how the air flows around a jet aeroplane, for example, or a water flows when a ship goes in a water, how the water goes around it, or the behavior of hurricanes or floods. They can be described in terms of Navier-Stokes equation. Yes?
What field is this?
This is related to what we call fluid dynamics. See, a lot of them are related to other fields, but some of them are pure mathematical too. But if you solve any of these, you're definitely advancing math, and you have to invent some new concepts in math, but you're also advancing other related concepts, whether it's computer science, quantum physics, or fluid dynamics. The fourth one, and it gets more and more abstract as you go on. The fourth one is called Hodge conjecture. Hodge conjecture. So what is Hodge conjecture? This is related to a field of mathematics called topology. Topology is a kind of geometry. It deals with surfaces, two-dimensional, three-dimensional, multi-dimensional surfaces. It's actually a very interesting one. In fact, talking about topology is a very interesting thing that we could do. Let me see if we can try to do this. So I'll take a slide. This for some students earlier, but let's see if we can do it. And you can do it at home later. Pretty easy to do. Okay, I'll take a strip of paper. Okay. So, if you put this together and combine this, you kind of make a circle, right?
Yeah.
And there are two surfaces that are formed. There's one surface outside and another surface inside. Okay? But how about if I give it a half twist? And now put it together here. Let me see if I can glue it together. I have glue here. So glue this one. Okay. All right. So if I put this here, what's so great about it? Aparna?
It's one surface.
It's one surface. Aparna, that's genius. That's what you guys meant into me said, right? So let's see. If I, what do you mean by it's one surface? Let's try to do one thing. Okay. In the earlier where we put that, we had an inner surface and outer surface, right? Let's start in the middle here. Okay. I'll start drawing at the middle of this. And you generally expect there should be inner surface and outer surface, right? Let's see. I start drawing this. Just continuing, right? Same straight line. Hey, see what happened? I covered outside but also covered inside and came back to the same thing. Go back and check it yourself. Just hold it and see. There is no outside and there is no inside. It's all one surface. Pass it to others. Right? Ashri?
I one time tried cutting it in half
Yeah?
and it made one loop against one another.
That's actually an interesting one. So if you take a regular circle, if you cut it in the middle, you will get two circles, right? Try this at home. This is called Mobius strip. Named after a German mathematician who first observed this. Mobius strip. And if you actually, like she said, if you cut in the middle, you will not get two different circles. You will get actually two circles that are kind of combined in the middle. They're twisted with each other. You cannot take them out without cutting it, without cutting in the middle, right? So this is a very interesting one. So this is a very easy example of topology. It becomes very complex, but it's a very interesting field. There's also something called Klein bottle. Go and check about Klein bottle. Klein bottle is a four-dimensional example of a Mobius strip.
Wait, what?
Yeah, go and check that out.
Silence, width, and breath.
Yeah, Kleine, Klein bottle. Go and check that out. You can check on the internet, and you can probably build one. So Klein bottle is so these strips. It takes a two-dimensional object and kind of now it's three-dimensional. Combined into one. A Klein bottle takes a three-dimensional into four dimensions. So a topology deals with things like that. Okay, it's a very interesting geometry, but it deals with surfaces of multidimensional surfaces. And in the 20th century, the great advances happened in the field of topology. But you know what mathematicians do when you make some advances? They want to solve higher order problems by making it more general. By making it more general, it becomes more abstract. And so after some time, so they try to describe topology in terms of algebra. We call them geometric algebra. Right? Because algebra is easier to, it's more abstract but easier to solve on a paper instead of using pictures. So, but here comes a mathematician called a Scottish mathematician called Hodge, Douglas Hodge. Again, Hodge proposed a particular hypothesis which you will not understand, right? But it's related to topology. And it says that, and hold your breath, you are not, a certain DRAM, D, it's not my name, R, it's RHAM. DRAM cohomology classes are actually combinations of certain algebraic cycles, and you should not understand any of that.
I
Right?
understand the algebra part, but not.
You understand at least one word, that's good. So that's called Hodge conjecture, which is unproven as of today. So you, these are very abstract to understand, but it's okay. Just know that there's something called Hodge conjecture related to topology, and maybe one day you can go and research more about it. The sixth one is called Birch Swinnerton Dyer conjecture. Each of them you can find more details about them. You can go to Clay Mathematics Institute website and find. And this one is related to what is known as elliptical curves. Now, if you guys remember elliptical curves, we talked about this last week a little bit. Do you remember? Andrew Wiles, while solving the Fermat's last theorem, he had to use this concept called elliptical curves. Yes?
What's the sixth one again?
It's called Birch, B-I-R-C-H, Birch Swinnerton, S-W-I-N-N-E-R-T-O-N, hyphen Dyer, D-Y-R. There are two, Birch and Swinnerton Dyer are two mathematicians who proposed this conjecture. Again, I will not try to explain what this is. This is related to the elliptical curves. And this again, each of these are advanced mathematical problems, and if you solve, you actually solve not just one problem but many related problems. And the last one, well, actually I changed the order as I said, just for convenience, but this one, the last one is, what I call as the last one is called Poincare conjecture. P-O-I-N-C-A-R-E. Now, if I don't tell how to pronounce it and ask you to pronounce, you'll probably say Poincare, right? It is actually pronounced as Poincare, like P-W-N, Poincare. Well, based on the pronunciation, can you guys guess which country he might be from?
Japan?
French.
France. The French names are got weird pronunciations. Poincare. The last E, for example, pronounced like A, Poincare, and O-A-N is a Poin. So, but apart from his pronunciation, he was actually, this is called a Poincare conjecture. Now, Poincare is a late 19th century mathematician, physician. In fact, he's called a polymath. In fact, many scientists call him the last polymath. Do you guys know what is a polymath? This is today what we call an anachronistic term. An anachronistic term is a term which does not belong to this time. And he lived up more than 100 years back, and he's called one of the yes, Pranay?
What is the field? It's from?
This is also related to topology. And in fact, Poincare is considered as one of the fathers of topology. He's actually one of the guys who established topology. The reason why he's called a polymath is someone who worked on who's an expert and a specialist in multiple fields, in math, physics, in fact he's considered the only other person other than Einstein, before Einstein, who came close to not necessarily inventing but understanding the theory of relativity before Einstein. He's a predecessor, he's probably a generation before Einstein. He lived from, I think, 1854 to 1912. Whereas Einstein actually proposed his theory of relativity in 1905. So he was probably in his 20s in 1905, but by the time Poincare is already old. He actually gave a series of, he's a Frenchman, and he's actually in the United States. He gave a series of lectures in the late 19th century, in 1880s and 90s, where he came close to talking about what we call a theory of relativity, although he did not fully reach there. So the great thing about Einstein's theory, the most math or science are built on other people, other research done by other people. For example, most of what you find, we talked about calculus, for example, Newton and Leibniz, when they found, it's not that they invented it out of thin air. For hundreds of years before them, in fact thousands of years, there are other mathematicians who found a little bit of that, and then Newton and Leibniz independently put it all together and called it calculus. And any inventions that happen are done by multiple people, by understanding, by taking one person's work, just like Riemann, right? You took the work of Euler as well as Carl Gauss and came up with the hypothesis. But a very rare set of scientific or math principles are almost single-handedly invented by one person. That's very rare. Most science does not happen like that. And theory of relativity is one such thing. Before Einstein, nobody was expecting it. Everybody thought all the laws of motion are governed by Newton's laws of motion, which was Newton discovered 200 years, 300 years before that. And by end of the 20th century, by end of the 19th century to around 1900, most scientists believed, in fact they said that science, everything that needs to be invented in science is already invented, discovered. At this point, it's only applying science to find new technologies, new devices, etc. But we all know everything about science. Well, that proved wrong within a few years. With in fact, completely two different things. One is Einstein's theory of relativity, which was completely unexpected, and the second one is what we call quantum physics. Because theory of relativity is related to very big things like the universe and the planets. The quantum physics is related to very small things.
Electrons.
Right, electrons, protons, the small things. But the point is, Poincaré probably is considered one of the only other person who came to kind of close to understanding theory of relativity before Einstein. So he's called a polymath. But he was also one of the fathers, one of the pioneers of topology. And nobody strip is interesting. In fact, topology goes back to that. And he conjectured, we will not understand his statement again, but he talked about something related to what he calls three-manifold. It's a term in topology. It's kind of a multi-dimensional surface. And he said that he actually asked a question. If the three-dimensional sphere, we all know about sphere, right? If the sphere is just characterized as the unique, you will not understand this term, as the unique, simply connected three-manifold. If you want to find more about it, you can Google this, it's called. And he asked the question, stop. And for more than 100 years, mathematicians tried to solve. Finally, this is the only problem solved as of today of the 7. This was solved in 2002. Just 2 years after that, Clay Mathematics Institute posed these seven as the greatest problem. Within 2 years of that, this was solved by a German mathematician called Gregory Perelman. But Gregory Perelman actually refused to take the $1 million.
What's his name again?
Gregory, G-R-I-G-O-R-I, Gregory Perelman, P-E-R-E-L-M-A-N. Yes, Steve.
I thought you said he was a Russian.
Yeah.
So did I say something else now?
German.
I'm sorry, Russian. Yeah. He's a Russian mathematician, Gregory Perelman, who actually proved this, and is accepted. In the Clay Mathematical Institute accepted. They announced the $1 million, but he refused to take it. The reason why he said he's not accepting is because it's interesting. It happens in math and science all the time, but he actually acknowledges that his work is based on work previously done by other mathematicians. There is another mathematician called Ricci, R-I-C-C-I, who actually came close to it, and Perelman used his theory to finally prove it. So Ricci probably deserves more credit than me, so I am not accepting this $1 million. Can you believe that? Are you? One day, you earn $1 million with your hard work, and you say, I don't want to take it because I actually used some of the theories proposed by others, so they deserve this more than me. That's what happens when you do some of the great things. Money is less important than those things, because now Gregory Perelman's name is etched in the history of mathematics forever, right, for doing that. So, I hope some of these stories inspire you, even if you don't understand all of it. In fact, you should not understand all of it at this time. But maybe you now understand, appreciate a little bit, so that a few years down the line, like under Wiles 20 years later, you come back and solve one of these. Yes?
If you do solve it, do you have to publish a book? Do you have to publish a book?
You don't have to publish a book, but usually when these things like these are solved, what you do is you write a paper, your proof, and send it to one of the journals. There are certain in each field of science, math, etc., there are certain journals published by renowned publications. You send it as a paper, and if they think, and that will often peer reviewed by others, and they accept and publish it, other mathematicians look at it. In fact, while it was 2002 when Perelman proved it, in 2010, 8 years after that, Clay Mathematics Institute finally said that we accept that proof, because it needs to wait for at least a few years for others to review it, peers to review it, and that yes, this proof is correct proof. Right? Just like for Mathus, if you remember Andrew Wiles, when he published, somebody proved it was actually there was a mistake in it, and 2 years later Andrew Wiles proved it. But after 80 years after Perelman proved it, it was accepted, and so it will probably take some. It's not that you published and you call Clay Mathematics Institute, oh, I got it, and they give you $1 million. You actually have to publish it in a journal, and other mathematicians review it, and they'll probably find faults. And you can correct the faults, you can republish again. But if there are no faults, like Perelman's theory, it will be accepted, and that's when you will be a possible. Okay? But before you leave, and it's almost time's up, but I want you to see this video for a few minutes.
Can I ask you a question, Brady? What is the most difficult way to earn $1 million?
Making YouTube videos.
Well, you probably know much more about that than I do. One of the most difficult ones is to solve one of the millennium problems in mathematics, which were set by the Clay Mathematical Institute in the year 2000. One of these problems is called the Riemann hypothesis, and it refers to a work of a German mathematician, Bernhard Riemann, which he did in the year 1859. So this is just one of the problems. In fact, there are 7, and only one of them has been solved so far. And interestingly enough, the person who solved the problem has declined the $1 million. So it just shows that mathematicians work on these problems not because they want to make some money. I think it is now the most famous problem in mathematics. It took the place of Fermat's last theorem, which was solved by Andrew Wiles and Richard Taylor in the mid-1990s.
But that wasn't a millennium problem.
That was not a millennium problem. The most essential thing here is what we call the Riemann zeta function. And the Riemann zeta function is a function, so a function is a rule which assigns to every value a certain number. A Riemann zeta function, it assigns a certain number to any value of s, and that number is given by the following series. 1 divided by 1 to the power s plus 1 divided by 2 to the power s plus 1 divided by 3 to the power s, 4 to the s, and so on. So, for example, if we set s equals 2, zeta of 2 is going to be 1 divided by 1 squared plus 1 divided by 2 squared plus 1 divided by 3 squared plus 1 divided by 4 squared, and so on. So, what is this? This is 1. This is 1 over 4, this is 1 over 9, 1 over 16. So this is an example of what mathematicians call a convergent series, which means that if you sum up the first n terms, you will get an answer which will get closer and closer to some number. And that number to which it approximates is called the limit. But the limit here is actually very interesting. And it has been a famous problem in mathematics to find that limit. It's called the Basel problem, named after the city of Basel in Switzerland. And this Basel problem was solved by a great mathematician, Leonhard Euler. And the answer is very surprising. What Euler showed is that this sums up to pi squared over 6. And so you may be wondering, what does this sum have to do with the circle? Why would pi, or pi squared, show up? But Euler came up with a beautiful proof. I'm not going to explain it now, but it's something which you can easily find online. This series is just one example of this Riemann zeta function, but you can try to do the same for any other value of s. So for example, if you take s equals 3, you will get the reciprocals of all the cubes, and you sum them up, and so on. So this will again be a convergent series, and you can wonder what the answer is. That would be zeta of 3. You can also try to substitute negative numbers. And this is very interesting, because if you just substitute s equals negative 1, then what are we going to get? So you will get 1 divided by 1 to the negative 1, plus 1 to the 2 to the negative 1, plus 1 to the 1 over 3 to the negative 1. If you take the reciprocal of something which is the inverse of something, then you will get that thing. So this will be 1, this will be 2, this will be 3, this will be 4. Does it look familiar?
Yes, I have seen that before.
We have arrived at the famous sum of all natural numbers, 1 plus 2 plus 3 plus 4. But you see, now we obtain it in the context of the zeta function. So this is what we call a divergent series. There is no obvious way how we could possibly assign a finite value to it. This sum is infinite. It does not converge to any finite value. But this context, if we put this value, this infinite sum, in the context of this function, there is actually a way to assign a value to s equals negative 1. And this is what Riemann explained in his paper. And so what Riemann said is that actually we should allow s to be not just a natural number, like for example 2 or 3 or 4, when the series is convergent, but we should allow also all possible real numbers. And not only real numbers, but also complex numbers. The way you get complex numbers is by realizing that within real numbers, you cannot find a square root of negative 1. So what to do? One way is to ban square root of negative 1 and say, this doesn't exist, we cannot use it. But in mathematics, we have understood a long time ago that actually there's a much better way to treat this square root of negative 1. We can simply adjoin it to the real numbers. Think of real numbers as points on a line. Here is 0, and here is 1, and here is 2, and then you can mark your favorite fractions. For example, 1/2 is exactly the middle way between 0 and 1, and say 1 and 1/3 would be sort of a third of the way between 1 and 2. But then you also have things like square root of 2, for example, somewhere here, and then there is pi, which is just to the right of 3. So all real numbers live here. Square root of negative 1 cannot be found anywhere on this line. But we don't give up. We say, you know what, let's actually draw a plane. Let's draw another coordinate system. And let's mark square root of negative 1 on this new coordinate axis. You see, if we do that, then every point on this plane becomes a number. So that would be 2 times square root of negative 1. Then if I take 3 times. But more than that, so let me find a number which is on the intersection of this line. I can draw a vertical line which goes from 2, and I can also draw a horizontal line. And there is this point of intersection. So this point also will represent a number which will be 2 plus 3 times square root of negative 1. So in other words, a general number is going to have what we call a real part. That's the projection onto this axis, and the imaginary part. That's the projection on the vertical one. The notation is a little bit clumsy. Instead of square root of negative 1, they write I. So then, for example, instead of writing 2 plus 3 square root of negative 1, we'll just write 2 plus 3i. It's an imaginary number. We imagine it. We cannot find it on this real line. So we have imagined it, and then we have adjoined it in our imagination. Real numbers comprise all points on the real line, on this axis, and complex numbers comprise all the points on this brown paper, if we could extend the brown paper all the way to infinity, right? So let's go back to Riemann. What Riemann's insight was that he said, look, let's think of this argument of the zeta function, this number s. Initially, we thought that s could be 2, 3, 4, and so on. But then we realized that actually any real number to the right of number 1, not including number 1, because actually in this case you cannot assign a value. It's a divergent series and it goes to infinity. But anything to the right, and I'm marking it with red, for all of them, this function is actually well defined.
You prove it or disprove it. What I mean by disproving is that over these 150 years since the Riemann hypothesis, if you remember the picture, many mathematicians try to find the place where they found many non-trivial zeros, and they found all of them on the critical line, okay, like the line is showed. So there was not a counterexample. So if you found a counterexample, do you know what is counterexample? An example is to say that all of them, everything that we found so far is actually on the critical line where real value is equal to half. But if you can find a point that is not over there but somewhere else, you just prove that Riemann hypothesis is wrong, right? Just like for Mathus last theorem, if you find a example where that number x power 12 plus y power 12 equal to z power 12, if you found numbers like that, you just prove that Fermat's last theorem was wrong. Similarly, if you find a counterexample where one of the zeros of this zeta function is outside that critical line, you can still make $1 million by just finding one counterexample. But many brightest mathematicians in the last 150 years tried and could not find, but maybe you can find. So you can either prove it or disprove it. You will still get $1 million. So you solve the problem one way or the other by either proving or disproving. By disproving, you mean that Riemann hypothesis is actually wrong. That Riemann was wrong, right? But so far nobody found it. I hope you guys enjoyed this, even if a lot of it went over your head. And hopefully remember a little bit this series of lectures that we did for the 6 weeks or 6 different sessions. I hope you will enjoy it. I hope you remember a little bit of that, and maybe one day, like Andrew Wiles, you a little bit of went into your dream and come back after 20 years to solve one of these, and there won't be anybody happier than me if you do that. But do remember, the most important thing about this series of summer program lectures that we did is to show you that there is a lot more in math beyond what you see in your school math. Okay? By saying that, I'm not asking you that school math is not important. It's actually very, very important, because to understand any of these problems, first you need to go step by step. You need to understand 1 plus 1 by 2, 1 plus 1 equal 2, like this go. And go understand everything that you need at grade level, but don't stop there, okay? Go a little bit beyond the skin deep to find more interesting ones. And we covered some of these actually in Math Genius a little bit to give you a glimpse of this. But irrespective, keep that and go back and watch these videos in case. Now you will forget after some time, and any time to do that, you go back and watch these videos. You'll get the links, your parents will get the links and watch again. And if you have any questions, you can reach me. You or your parents can call me or email me. And one day we'll probably start the Riemann Club, and I hope you'll join the Riemann Club membership. Okay? Any questions? If not, have a good night, and probably you'll start the school in a couple of weeks, and some of you, I'm sure I will see you next week onwards on the Genius class or Math class better. Otherwise, have a good rest of the summer.